After that we have another one is like a blowout or raking out. So, it is the process to stop the furnace at the end of its campaign. So, now we had now 3 of the things. One is fanning, where just for emergencies you want to shut it down for few hours like that. It is not used for the long purpose. And then we have a back drafting, which is used a little longer than the fanning purpose for maintenance and others. And then we had the banking one, where large time is required. So, you goes for it goes for days. So, when you need this thing for days to shut it down the blast furnace, that time banking is required. And when finally you have to shut it down, let us say for relining or the furnace life is over, then we go for this blowout and raking out operation. So, in this process at the end of, so it is done in 2 ways. One is charging is stopped and the stock is allowed to descend until minimum of it remains inside. As the stock sinks, blast is reduced and the top of the stock is cooled by water spray inserted through the top. So, remember in this one water spraying started from the top to cool the charge at the stock line. So, to begin with, burden quality is altered to produce highly siliceous slag. So, which means you put this silicon gravel or quartz in that. The furnace is isolated from the gas cleaning system midway through the blowout. The last cast is carried out as completely as possible. Towards the end, the remaining stock is quenched with water and the furnace becomes cold in about 24 hours for the crew to start the raking operation. So, this raking out is coming from this raking operation when the personnel starts this operation. So, here you use the water spray to cool it down, and of course, after and naturally again use highly siliceous slag towards the end of it, as we do in the blow in the starting. Here towards the end you use the siliceous slag which can easily pass through that, and the furnace is isolated in the midway through that. In the second one, so in alternative method, the blowing out start with a blank coke charge followed by a charge of clean silica gravel of 25 millimeter and up to 50 millimeter in size. So, it starts with this material from the starting. The stock line is kept at the normal level in the beginning, but later on it is allowed to sink. Water is sparingly used to control the stock line temperature. The blast volume is not reduced to the extent done in the previous method. So, in the previous method we reduced the blast volume quite a lot, but in this one you do not do that much. The leftover gravels are washed out with water in the end. The time required to blow out is very short, generally about 6 to 8 hours in this case. So, this is a very quick method, and usually burden composition should be able to produce more siliceous slag, because anyway you are putting silica gravels. So, that lime can be removed as much as possible, because it creates problem later. when it comes in contact with water by forming calcium hydroxide, which can generate sufficient force to crack the steel hard shell. So, essentially why we are saying more siliceous slag, we really do not want to have any lime in this slag, because when you put the water in this, so calcium oxide will water gives you calcium hydroxide, and that because expand even such gas are also with there, and due to expansion of that it exerts the force. So, and when there is a plenty of lime in that, that force could be of sufficient force, and it can even crack the steel hard shell, and sometimes even the small explosions occur if that force is not taken care in a proper way. So, it is very essential step that as much as possible the lime should be removed by end of the blowout period. These are some of the figures which show the operation which we had discussed previously. So, after emptying the hearth from liquid, the following step can be used as guidelines. So, as shown in below in the below figure, to shut down the furnace. So, reduce the blast when you are shutting it down to minimum blower volume at 100 meter cube per minute. Then somewhere after half an hour you stop the tuer injectant if you are having a oil fuel or the gaseous fuel or PCI anything, and then you stop that one. Stop charging and check furnace when tuer is empty. When the furnace is empty, then almost after 35 minutes you start reducing the blast to 30 kilopascal with the snot at 150 meter cube per minute. So, at blast pressure when it reaches 30 kPa, open bleeders and isolate gas cleaning system, remove all blast airs, open backdraft, open peep sight and back doors, and that is where when things are over, this one can say its furnace has been shut down and other operation can be started. Similarly, for short shutdown, if somebody want, then the following procedure may be used to restart the furnace. So, this is after a short shutdown like drafting or banking, then how to restart the furnace. So, open the tuers and insert. So, this is after tapping out all the material and things, you are starting again from that time. So, open tuers and insert PCI lenses, prepare cast house equipment, first cast with diameter plus 10 millimeter, put blast on. So, this is happening your within 10 to 20 minutes. So, put blast on furnace and increase to 30 kPa, connect gas cleaning plant and close bleeders and start charging. Increase blast volume to 100 meter cube per minute until 60% target is reached by 50 minutes or so. So, at 60% target, wait for the Verdun descent, start tapping. When Verdun descends, start PCI and oxygen at that time, and increase the blast volume to 200 meter cube per minute until 80% of target blast volume is reached, which is usually achieved in an hour or so. And after that, you increase slowly the blast volume with 5 meter cube per minute until the 90% of target you reach in sort of 2.5 hours, and then you increase the blast volume very slowly after that to 2.5 meter cube per minute until the 100% target is reached on the blast furnace. So, which if you look at the minute, it can take about 6 hours or so. So, in 6 hours you can bring the furnace again to the normal operation, or 6 to 8 hours when it is shut down for a short period of time. And this we have you have seen this one figure that after relining or blowing, what sort of how the silicon content and hot metal temperature behaves. In this one you have more parameters. So, one is the blast volume and time is given in hours. So, in 2 days you can see your blast volume, which is going with 1000 meter cube per hour. It goes in 48 hours to the normal one, and similarly your silicon percent content also fluctuate and reaches to its a normal silicon percent content. Your tears open slowly and reaches to the normal operation, and coke rate is also from very high 750, then it reaches to almost 420 or 410 kg per ton of hot metal. So, when these sort of target values are reached, then one can say the furnace had achieved the normal operation, which takes almost 2 to 2.5 days. So, this is all about the how to start the furnace, how to shut down the furnace, how to stop the furnace in between, and then how to restart the furnace in between. So, it can take care of various situations, various conditions which are occurring during the plant, and it is important to handle all these problems. So, now I hope you understand how these operation works in different conditions. So, after this we will move on to the another important aspect of the blast furnace. It is about the irregularities in the blast furnace. This is again a very important thing to know in the blast furnace. What are the irregularities? In fact, many of these irregularities we have talked during the span of this course at various stages, and so some of the things will not be repeated here, some might be repeated, and something which are new would be discussed in this one. So, abnormality or irregularity in the blast furnace production can develop due to either faulty mechanical devices such as bulb, cooler, or faulty operations such as charging and tapping, or undesirable physico-chemical changes in the blast furnace. So, it can occur by any of these or with the combination of these, and when that happens, you face the abnormality or irregularity in the operation of the blast furnace. So, as I mentioned, some of these irregularities and their remedies have been discussed before in detail. Some are mentioned below, some have been repeated. So, one important irregularity is about scaffolding. So, it is a large chunk of charge that gets stuck to the furnace wall, particularly in the boss region, due to the presence of alkali, which condense on the brick lining, forming a low melting alkali aluminosilicate, to which charged particles stick progressively. So, this is mostly caused by the presence of alkalis, And because when you are charging the furnace, fines are also generated and things, and when this material becomes quite soft, these fines and other things can accumulate on this, and then it progressively increases in size. So, the presence of alkali is the main reason of having accretion development and due to this brick lining. So, indication of this, because it is increasing progressively, naturally rise in the blast pressure, increase in dust losses, increase in fuel consumption, excuse me, increase in top gas temperature, uneven movement of the burden, increase in output. So, essentially the scaffolding is also reducing the area of the furnace. So, if these things are happening, this gives an indication that scaffolding is happening somewhere in the blast furnace, and one has to look at all these things and take the corrective action. So, what are the corrective actions for this? Decrease the alkali content, which comes mostly from the coke, sometimes with some ore. So, low alkali content material must be charged. Lower the flame temperature, because by that one is vaporized and then goes up and condenses near that. So, lower the flame temperature. Change in charging sequence, compact bricks with low porosity. So, brick lining should be much compact with a low porosity, that they cannot be attacked by alkalis. So, that softening will not occur. And finally, the destruction of scaffold with explosive. When it does not go, then explosive has to be used to remove the scaffolding. So, these are some of the remedies by which scaffolding can be reduced, but because alkali is the most important factor. So, this slide shows how the recirculation of alkalis occur, though we had discussed this one in our previous lectures in the starting, but here we are again discussing and giving a little broad view of it. So, this is the here is the example of potassium, same thing is applicable for the sodium. So, input potassium silicate from the coal. So, from a coal actually is the source and even the coke. So, when and then they react. So, K2CO3 which is coming, it actually at this temperature around here from K2O, and K2O can dissolve at this boundary because this is just the starting of the melting, can dissolve with the slag actually at 1300 degree Celsius, and also this K2O coming here. So, it can actually become an elemental potassium almost at 1350 degree Celsius and some or sodium element, and this is like a vapor. So, it is vaporized, and so here temperature becomes low, it condenses here, goes with this slag, again it is coming and vaporizing, and some of this potassium or sodium is combining with the slag. So, comes out with the slag a bit, and some of them is going out, and naturally some of them, if the flow is not proper, some of them they attack the refractories over here, high temperature zone, they can form the silicate, low melting silicate by reacting with this, and fines which are generated, they stick to it, and slowly this increase in size. So, it can increase in size, and then it will obstruct all the gas flow, reduce the volume, temperature will become higher, as we had mentioned in the previous slide. And sometime it can also, because nitrogen is always there, it can form the cyanide, and that cyanide again react with the CO2 in this region, in the stroke region, and it forms, go back to K2O, into K2S and then to K2O. So, naturally, if you look at that one way of reducing it, if you can have a central gas flow. So, from the top gases, it can from the center, it can go out to the top gases. Peripheral flow will attack the bricks, and then more of scaffolding, promoting that in that way. So, some remedies are again retention of effects by slag basicity and temperature. Now, lower the slag basicity helps in removing the alkali, but remember you, with slag basicity, sulfur content is also depend. So, one has to make a judicious choice of the basicity, and lower the temperature, less FeO is removed from the slag and less alkalis are reduced. So, now here two conflicting again the things, to lower the temperature, then FeO removed from the slag would be less. So, you are losing more FeO with the slag. On the other hand, the alkalis are not that much reduced. So, they go with the slag and they can be removed. So, again a optimum or compromise has to be made between these two and see. So, however, when alkali content has increased, probably that time you may go for a less FeO removal, because you want to remove that, and then again you can start or resume the normal operation of the blast furnace. And central gas flow helps in removing the alkalis. So, as I mentioned in the previous slide, if it is a central gas flow by changing the charging and other ways you can achieve this, which we had discussed before, then you may reduce the alkali content in the charge, and thus you can minimize the scaffolding of it. Another one is escapes. The buildup of concentration of fines close to the wall is difficult to reduce and melt, which travels down and can be observed as non-molten material through the pip sites near the tuer known as escape. So, essentially what it is, when you are charging the material, if it is hitting the wall, it will generate fines, more fines, and that fines get accumulated as a sort of a material chunk, and because this is very fine, so porosity is less, so reducibility is also less, and that one actually travels down with the charge, a charge travels, and if it is not melted and reduced further as it is going down, which is quite difficult because it is a very fine material. Sometimes of course, this can stick to the scaffolding, and sometimes it travels down, and it travels down up to here this schematic shows actually. So, here the buildup of those fines which is traveling down hasn't reduced much, and finally it hasn't melted and reduced that much. It has reached to the tuer region and probably in front of the tuer, and that is a big mass chunk and it is blocking the tuer, sending back whatever is coming from the tuer out, and that creates a dangerous situation and some explosion may occur in the pipe. So, these things happen sometime if this is not taken care, and it is quite dangerous. So, the remedy of that indication is increase in the flame temperature, non-uniform gas distribution. Naturally, it is blocking one of the tuers, so there would be a non-uniform gas distribution, change in chemical composition of the slag. So, remedy is use proper charging equipment, well-less charging, avoid wall hitting by the charge. So, well-less charging actually gives you this advantage that it does not hit the wall. So, less chances of creating the fines, and so mostly it is more about the quality of the charge should be strong enough, and the proper charging equipment should be used starting from the storage bin to dumping it. Another abnormality is hanging, that is slips or hanging and slips. These are two things I said, but we will discuss because they are related. So, when a regular charge distribution is disturbed due to the presence of wedging, of bridging or scaffolding, then hanging occurs. Top hanging occurs mainly due to the carbon deposition reaction. See, due to the we discussed this one solution loss reaction where the carbon deposition occur, and that carbon deposition when this occurs, it hinders the descent of the charge. So, and this may occur in the top section. So, top hanging occurs mainly due to the carbon deposition reaction, bottom hanging occurs in the Boss region due to the slag quality, escape formation, etc. Normal hanging can occur anywhere where you have a low voidage. So, when low voidage are there, anywhere that normal hanging can occur. Remedies: add more limestone, higher flame temperature in this one. This I am not also talking much because we have talked about it. In fact, we have discussed with some of the figures also how this bridge is forming and hanging is occur, and below this the void space is created, and when it is unable to withstand that pressure, suddenly the whole chunk is slipping down, and that is where the slips come. So, collapse of hanging result in sudden sinking of burden known as slip. Therefore, main cause of slipping is hanging, which may result in chilling of the hearth in extreme condition. In extreme case this can happen. So, this is very important, that hanging and slip, and we had discussed this thing before. So, I am not discussing much. You can go back to some of those slides and can have a look at it. Another abnormality is about the chilled hearth. So, just now we say in the slips extreme condition, it may happen that due to slipping of the chunk mass, it can fall into the hearth, and hearth chilling can occur. The sudden temperature drop of the hearth is known as hearth chilling, which may occur due to the slip phenomenon, excess moisture in the blast, etc. So, reasons are sudden slips of the cold material, leaking of Boss and hearth cooling plate, that is also very important, and very often it happens. Collapse of cold material through large channel, excessive moisture in the blast. If excessive moisture in the blast, then the temperature reduces, and which also results to the chilling of the hearth. Remedies: high flame temperature one should have, high fuel rate through the tuya, low moisture blast, no water leakage, so properly sealed. These are the sort of some remedies of chilled hearth. Another one abnormalities or irregularities is pillaring. So, formation of cold central column of the stove with an annular zone, annular hot zone. So, this is if we go back to here, this is mostly if your this center region has a less voidage, in that the charging in something such that you have a less voidage here, then the reduction and heat transfer would be low here, and this will form like a pillar here, and that is what which we are talking about. So, it is a bad it causes due to the bad charging sequence, low voidage in the central region, peripheral flow of the gases. So, remedies: change the charge sequence to get more central flow of gas, more penetration of raceway in the horizontal direction. So, that is increase in blast pressure. So, when you increase in the blast pressure, so raceway the raceway penetration will increase more in the horizontal direction, which will promote the central gas flow. So, that will help in better heat transfer and mass transfer. So, that may not occur, and one of the reason of hearth chilling, because when that mass becomes very high, suddenly it can collapse into the hearth and hearth chilling may occur. Another one is about the circumferential symmetry. This is one important one again. For high productivity, all tuyers must contribute equally to the process. So, this figure shows one normal operation where all the tuyers are operating, and you can see a very good circumferential symmetry in all respect. Now, in this figure, one tuyer is off, suddenly you can see the imbalance over here. So, that is the tuyer which is off. So, that is giving a quite uneven circumferential symmetry, and that is going to create quite a bit problem. One, due to uneven of this symmetry, you can have a asymmetry cohesive zone. So, the one side has a quite low, other side has higher side. So, this is again is going to create a big problem in the running the blast furnace smoothly. And so, asymmetry flow can arise due to asymmetry in charging, blast distribution, worn refractory uneven coal injection at the tuyer even. At one tuyer you are injecting 50 kg per ton of hot metal, and then from another one you are injecting 200 kg PCI per ton of hot metal, and that uneven coal injection is going to lead the asymmetry problem in the blast furnace. So, this whole thing must be taken care of in a proper way. Other irregularities which are there in the blast furnace are channeling, flooding, failure of equipment like choking of gas offtake, cooler failure. We are of course not talking mechanical side of the things anywhere in this course. So, this is another different sort of phenomena which is not much related to the iron making process. So, this is more due to the mechanical failure and other things, but the channeling and flooding is very common phenomena which occurs, and fluidization, and this we have discussed in great details in some of the lectures. So, you should go back into that and try to understand channeling, flooding, fluidization, loading, all those things because these are very common irregularities in the blast furnace, what we had discussed previously, irregularities, because that anytime anywhere can occur, and that can lead to uneven operation of the blast furnace. So, some of the above mentioned irregularities have been discussed before and hence not repeated here. So, I would suggest please go through the previous lectures and check this one, because these are very important irregularities and which very often occurs in any of the blast furnace, and how to remove those irregularities or how to correct that, that is also discussed in those lectures.